Before I do, let me digress for a moment and tell you a little bit about diagnostics in the United States. Okay, so straight up, before I get into the, how much all this costs, I have to tell you that this is a topic that's really near and dear to my heart for a very personal reason. My father passed away from lung cancer about 6 years ago, and he died at the age of 58 from lung cancer. Never smoked in his life. Okay, and this is astonishing to me because my father was a physician, and if anyone was receiving the world's best medical care, it was my father. All of his friends were physicians. He was constantly, looking at small scrapes on his elbows and stuff like that. This is a guy who really spent a lot of his life looking at bodies and doing diagnostics. And by the time the lung cancer was diagnosed, it was already stage 4 metastatic. It was too late. Okay, so my thought is, and the reason why at that point I just turned around the lab and I said, we have to do something about this. And the reason for that is I feel like we can do diagnostics a lot better than we're doing now. All right, and I'll show you exactly what I mean by that. So in 2005, the US spent about $2 trillion on healthcare, which is an enormous number. But if you actually look at the breakdown of that $2 trillion, you find some surprising things. For one thing, pharmaceuticals, it turns out, are a fairly small percentage. They're only 10% of this $2 trillion. Okay, so that's a little bit surprising because people put a lot of emphasis on lowering drug costs. But really, the big money is in this other care category. So that includes things like doctor visits and hospital stays and things like that. That's where most of your money goes. It turns out that a vanishingly small percentage of that goes to diagnostics. Diagnostics are actually less than 2% of the $2 trillion that we spend on healthcare in the US. It's really a tiny little percentage over here. And so our thought is, if we can actually reduce costs and at the same time improve the treatment of patients if we had better diagnostics in this country. If we can get the disease early, then there'll be a lot less suffering from the treatment and you'll be a lot more likely to survive. Okay, if we can catch cancer at the single cell stage, that would be a really big deal. So that's what we want to do. Okay, now let me also show you in a little greater detail where I want to drive this. So currently, when we look at cancer, when we do diagnosis of cancer, you're actually pretty lucky if you do an annual check for cancer diagnostics, for cancer markers. Okay, in fact, that's coming soon to you. Eventually, you'll get to the point where, say, every year when you go to visit your physician, in the physician's office, they'll actually check you for a series of cancer markers. And again, you'll be lucky if you get an annual snapshot of cancer marker levels. What I want to do is I want to invent technologies that will really shift this paradigm. Instead of going for an annual check for cancer markers, I'm envisioning things, and my colleague Reg Penner is envisioning things that will let us move to a daily type of check. Specifically, I want to do this. I want to be able to look at every single day the cancer marker levels and look for trends at a daily basis. If we can catch those trends early, then we'd have a way of diagnosing the disease. Okay, now the truth is, there's no technology that lets us do this. Okay, really, I mean, what I'm asking for is I'm asking for the equivalent of this wondrous gadget, this cell phone, to be able to interface with biology and check for cancer markers. And there's really no technology that does that, right? The circuits in here don't interface at all with biological systems. There's no way that the circuits in here can talk to the cells in your body and tell you whether or not you have a cancer marker. This is where the chemistry comes in, because I can't turn to my colleagues in engineering and tell them, build me this device. The basics, the fundamentals are just not established yet. And so that's where our laboratories here at UC Irvine have to go out and invent the new technologies that will then make that sort of vision a reality. That's chemistry. Okay, so here specifically is what I want to get towards. I want to get towards daily diagnostics using viruses that are wired into electronics. Viruses are useful because we can get exquisite specificities for binding to cancer markers. And what we're trying to do is build devices that are based on nanometer scale wires that will allow direct electric, real-time, reagent-free detection of a specific molecule, essentially any molecule. And I'll show you some evidence that we're moving in that direction very shortly. Okay? The advantages of this is we're talking about really tiny little devices, and because they're small, they'll be very power efficient and even very inexpensive. And that's really what you need. We need something where when you wake up in the morning and you go to the bathroom, in your urine, there's an immediate test for cancer markers. And if we can do that in an inexpensive manner, then it actually might become a reality. Okay, so that's what we're driving towards, daily diagnostics. All right, so that's what we need to invent. So going towards that goal, the first challenge is how are we going to recognize the cancer markers? Because again, electronics currently do not interface with the biological world. So the first thing we have to do is to come up with a way of recognizing when we find cancer-associated molecules in, say, urine. Okay, so to do this, we use a technology called phage display. And here's the way this works. So you remember that harmless virus that I told you about earlier that infects only bacteria? Here it is. Here's a close-up view of this. This is a scanning electron micrograph. Oh, by the way, over here, do you see this little cluster of grapes? That's the head of the virus. That's what it uses to attach onto its host. And then the length of the virus all the way along here is chock full of DNA. This thing is just stuffed solid. It's basically a delivery vehicle for DNA. But this virus is completely harmless. So manipulating the DNA that's encapsulated here, we can convince this virus to display out here a non-viral protein. So we actually will alter the surface of the virus. So now it has a protein that it usually doesn't have stuck out on its surface. We have this foreign protein stuck out on the surface of the virus. The truth is, the virus doesn't really care. It shrugs. It goes about its viral business. It looks for a new host to infect, and it keeps going. It doesn't really care one way or another if it has the foreign thing out there on its surface. Now, here's the reason why these viruses are so useful. You remember earlier I told you there's this huge diversity of viruses on this planet? So using very straightforward biological and chemical techniques, we can readily fabricate a giant collection of these viruses. I can make, or actually graduate students and undergraduates in my laboratory can make around 1 trillion different viruses. And I teach an undergraduate class, an upper division laboratory class, and at the end of the class, everyone's made 1 trillion different molecules using this technique. And that's really cool because it turns out it'd be really hard to make 1 trillion different anything using any other technique. Okay, so the viruses do all the hard work for us. Now, here's the advantage of tethering things to the surface of the virus. Viruses have this tremendous will to propagate their genomes. That's what I told you about earlier, how they're looking for new hosts to infect. So we take advantage of that will to select for some viruses that do stuff that's special in that giant collection of trillions. So for example, we can do selections for binding to this Pac-Man-shaped receptor. And we'll pick out of this giant collection just the few that stick to Pac-Man over here, wash away all the non-binders. So all these guys over here that don't stick get thrown into the trash, washed down the drain. And all the ones that do work are amplified up in the host for this virus. The host happens to be E. coli, a harmless bacteria. If we do this several times, we'll select for the few. So we do this process of bind, wash away non-binders, amplify, and do this several times in a row. We will amplify and enrich for the few members of the library that can stick to, say, this Pac-Man-shaped molecule. If the Pac-Man-shaped molecule is a cancer-associated protein, this gives us a powerful way to identify binders against cancer. This gives us a way of identifying cancer cells and discriminating between the cancer cells from the non-cancer cells.